あ、あります。自分の持ってます。あ、あります。あ、ええ、お任せします。はい、そうです。
Okay, so good afternoon. So last talk of this week is François Rugal from Kyoto University. So he is going to talk about average case quantum advantage for shallow circuits. Okay, please.
Okay, thank you. So I will talk about quantum supremacy. So I put quotation marks here because there are a lot of debates about the word supremacy. Maybe you should better use the word advantage instead of it. But I will use supremacy for this talk. So very roughly speaking, the goal is to find some computational task that can be solved easily in the quantum setting, so now or in the near future, but that are hard to solve in the classical setting. Okay, very rough. And the first time I heard about this goal, I thought, well, we already have many such tasks. Quantum key distribution, you can do it, even in the lab. And it's impossible to do classically. Quantum games, also we can do it in the lab. And you cannot obtain the same success probability classically. Quantum fingerprinting and many other tasks involving quantum communication. We can prove exponential gaps between the amount of resource needed in the classical and quantum settings. But the point is that quantum supremacy is about the circuit model, or at least the usual version of quantum supremacy is about the circuit model, because what we care is building a quantum computer. And then, so we cannot use this task, and what should we use? What kind of task? So we don't have any really useful task that can be a candidate for establish this, but it's not a big issue for now. Let's concentrate. It will be okay for us if the task is not really useful. So let's forget about finding a useful task that can be solved efficiently in the quantum setting, but not in the classical setting, and let's try to find any task that achieve these goals. And there are many indeed good candidates. Boson sampling, IQP, random circuit sampling. So many candidates have been proposed in the past years. But the point is that all the prior works, or most of the prior works, for the proof of the classical hardness, so they give a computational task, they show it can be computed easily in the classical setting, even with a very few resources, but also show that you cannot do it efficiently classically. But the proof of the classical hardness relies on conjecture or complexity theoretic assumptions. So conjecture, for example, anti-concentration conjecture. Complexity theoretic assumptions, some kind of generalization of P not equal to NP. So for example, the polynomial hierarchy does not collapse. This kind of conjectures. So they are really well-believed conjectures, but an interesting question is whether you can establish quantum supremacy without relying on any conjecture or assumption. Okay? And a few years ago, Bravik, Gosset, and Koenig gave one of the first examples of quantum supremacy without any conjecture or assumption. So they show that there exists a computational problem that can be solved by a very weak quantum circuit. So more precisely, there is a quantum circuit with constant depths. So we call this a shallow quantum circuit that solves this problem on all inputs. But any class, so this problem cannot be solved with a classical shallow circuit. So if you ask to solve the problem in the classical setting, you cannot do it with a circuit of constant depth. So this gives you a separation between the power of shallow quantum circuit and shallow classical circuits. And there is no conjecture here, no complexity theoretic assumption. It's really an unconditional proof. Okay. So in this work, we show this result. It's essentially the same, but there is a difference here. So here, this theorem shows that if you want to solve the problem on all inputs classically, you cannot do it with constant depth. In our version, we show that even solving it on a non-negligible fraction of the inputs cannot be done classically in constant depth. So what we obtain here is an average case classical hardness, while the original version was a worst case classical hardness result. So we obtain a stronger evidence of quantum supremacy here. And it's without any assumption, any conjecture. Okay? And I should mention that several similar results have been obtained independently by many other researchers. At least there are 3 papers proving very similar things. So I will come back at the very end of the talk to the relation between this version and the version proposed in the other works. Okay? Okay. So, and if you have any question, please don't hesitate to interrupt and ask. Yes? If you have any question, please don't hesitate.
Is that like outlawed by
It's very possible, but we don't have a formal, I don't think there is a formal proof of that.
So that would count as a computational task, though. It's not
This
like
would be a computational task, but what do you mean by simulating?
well, like just so if I have some analog quantum system and I'm able to manipulate it to some target Hamiltonian, then I could just like watch it, and then you could extract it.
Yeah, so what I mean is a computational task with a classical input and a classical output.
Right. So
I give you, say, maybe you would.
yeah, well, I'll talk after.
Yeah. And for that, we have many evidence. Indeed, simulating a quantum circuit seems very hard, but we don't know how to prove mathematically that it is hard. It's the same as proving P not equal NP or things like that. Everybody believes that it is true. I believe that it is true, but it's not a mathematical proof. Okay. So I will, we will use a lot of graph states. So you already, I think, there was a few talks dealing with graph states. So I have only one slide explaining the concept. So basically, a graph state corresponding to some graph is what you get when you prepare for each node of the graph a state in the qubit in this state, and you apply a control Z operation on the qubit corresponding to each edge. Okay, so this is a control Z operation, depicted like this, or this is the same. So let's say an example. Here you have 6 vertices, okay, 6 nodes. So I prepare 6 qubits, and I prepare them in this state. So I apply another gate here. And then I have 1, 2, 3, 4, 5, 6, 7 edges. So I need to apply 7 control Z operations. And this is what I do here. So you see, for example, corresponding to this edge, I have this control Z operation, qubit number 1 and 2. And to this one, this is the operation between qubit 4 and 5. Okay? So 1 qubit for each node, and you apply a CZ operation for each edge. And this gives you what we call a graph state. Okay. So now I will explain one fairly old prior work, which is really the basis for all the theory that I will present today. So it's a fairly old work from 2007 by Barrett, Caves, Easton, Elliott, and Pironio. And what they consider a circle, a ring of length n. Okay, so n nodes. And n is a multiple of 3. So you can see it as a triangle. Okay? So triangle with 3 sides, each of sides n over 3. So this picture represents the case n equal 80. Okay, so now I will define a computational problem based on this graph. So each corner of the graph will receive as an input a bit. Okay, so there are 3 corners, so you have 3 bits. Here, this node will receive B1, this node receives B2, this node receives B3. And each node will need to output a bit. So after the computation, each node will output a bit. So here there are 18 nodes, so there will be 18 bits as output. And let me explain the relation between the input and the output. So we consider the following process. Okay. So all the nodes prepare the graph state corresponding to the whole triangle. Okay, it's a triangle, so it's defined a graph state. So each node prepare 1 qubit. Each node has 1 qubit, and they apply a control Z operation. Each neighbor's nodes apply a control Z operation. So this gives the graph state corresponding to the whole triangle. And then each node, which is not a corner, will measure its qubit in the x basis. So you measure your qubit in the x basis. And you have an outcome. It's 0 or 1. 0 with some probability, 1 with some probability. And you output this bit. And each corner node does something similar, but there is a small difference. Is that the measurement basis depends on its input bit. So for example, this one, depending on the value of B1, choose the basis as follows. So if B1 is equal to 0, then it measures in the x basis. If B1 is equal to 1, it measures in the y basis. Okay? And this gives, again, 1 bit for the measurement outcome, and the node outputs this bit. Okay, so you have this process. Okay? And I'm claiming that this process, this quantum process, samples from the uniform distribution over all binary strings satisfying the following conditions. Where M odd, MR, MB, ML are this. So let's explain what they are. They are bits. MR is 1 bit. MR is a bit corresponding to the parity of the outputs of the nodes of even index on the right. That's why you have R here. So you look on the right side, and you look at the output corresponding to the nodes of even index. Z2, Z4, Z6. You take the parity, and this gives you MR. MB. B is for bottom. Similarly, it's the parity of all the outputs of the node of even index on the bottom. So Z12, 10, 8 here. And ML is the same on the left. So here, 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 the parity of this. And M odd is the parity of everything else. And what I'm claiming is that if you look at the output distribution of all these 18 bits, they satisfy this condition. So this corresponds to a uniform distribution over all binary strings satisfying one of the 4 linear equations here. And which linear equation is satisfied depends on the input. If the input is 0, 0, 0, this is this one. If 1, 1, 0, this is this one. And so on. Okay? So maybe we can work out one example, very simple. N equals 6. So N equals 6. You have this. So you have B1, B2, B3, and the output Z1, Z2, Z3, Z4, Z5, Z6. If you consider the case B1 equal B2 equal B3 is equal to 0. So if you consider this case, it's the first case. The claim is that M odd is equal to 0. So the claim says that M odd is equal to 0. So what is M odd? Is the sum of the parity of bits with odd index. So Z1 plus Z3 plus Z5 equals 0. Okay? So this is a claim. Why? The reason is very simple. Because Z1, so this node So if everything is 0, what you are doing, you are measuring everything in the x basis here. So if you look the measurement operator, this measurement operator is in the stabilizer. Stabilizer. Okay? So this means that the output is always 0. Okay? So the product, well, if you consider that the measurement are 0 or 1, the parity is equal to 0. Okay? If you consider that the measurement outcome is 1 or minus 1, this means that the product is equal to 1. So it's equivalent here in the case we're considering that the output is a bit 0 or 1. The parity will be equal to 0. And if you have, say, B1 equal B2 equal 1 and B3 equal 0, then this corresponds to measuring here, here, B2 here, and here. So the claim is that M odd plus MR is equal to 1. So this corresponds to Z1 plus Z3 plus Z5 plus MR is Z2. And why? Because in that case, here we are measuring the y basis, x basis, x basis. And indeed, if you look at the measurement outcome, so y1, and why? Because in that case, here we are measuring the y basis, x basis, x basis. And indeed, if you look at this thing, so the negation of this is in the stabilizer. So that's why you get a 1 here. Okay. So it's really just a general theory of measuring graph states. When the measurement operator is in the stabilizer, the parity of the measurement is always 0. And when the negative inverse is in the stabilizer, you get a 1. Okay, it's only, this is what expressed here. Okay? It's a very simple result from the analysis of stabilizer states. This is what expressed here. Okay. So if you do this, what you get is this. Uniform distribution over all binary strings satisfying one of the 4 conditions depending on the input. Very standard. So if you do this, what you get is this. Uniform distribution over all binary strings satisfying one of the 4 conditions depending on the input. For the other one, what you get, you don't obtain anything interesting. So you obtain a random output. Okay? And we won't use it later because there is no correlation there. So I don't care about what will happen when it's not the case. For the other one, what you get, you don't obtain anything. Okay, so let's see a little bit how to implement this process. So first, the main thing that you need to do is to prepare the graph state. So preparing the graph state is very easy. So each node can simply create a qubit, okay, in the state plus, ket plus, and then you can simply talk with the neighbors in order to apply a control Z. So it can be implemented very efficiently simply by communicating with the nearest neighbors. Very efficiently. And measurement, no communication, no communication. So this process can be implemented extremely easy. You simply need to create the graph state. And graph state is some kind of local entanglement. You simply need to make an entanglement with your neighbor. So you can do it very efficiently. So now what is extremely interesting is a claim 2. So claim 2 says that any classical protocol that samples, or even approximately from this distribution, requires long-distance communication. So why? So the proof is extremely easy and very beautiful. So assume that you have a classical protocol. Okay, so each node has each corner has an input, and the node together want to sample from the distribution satisfying this. So assume that the protocol does not use long-distance communication. More precisely, there is no communication between two nodes located at distance at most larger than n over 6. So then, what can we say? The first thing is that MR. So MR is here, the parity of the output of the node of even index on the right. So here, the parity of this. The simple thing that we can say is that MR cannot depend on B3. Why? Because B3 is here. It's very far from the right side. So if you don't have long distance communication, the information about B3 cannot reach the right side. So MR cannot depend on B3. The first thing. Okay? The second thing, MR is an affine function of B1 and B2. Why? Because you cannot have, when you look at MR, you cannot have the product of B1 and B2. Because the side here, the length, is n over 3. So in order to obtain the product, you need to have the information of B1 and B2 reaching at one point. And you cannot do it if you have communication at distance less than n over 6. Okay? It will require n over 6 distance in order to send all the information to an intermediate node. So MR is an affine function of B1 and B2. And similarly, MB is an affine function of B2 and B3. ML is an affine function of B1 and B3. And MOD, all the remaining thing, it may depend on the 3, sure, but it's still affine. So you don't have any product term appearing here. Okay? So for any classical protocol that does not use long-distance communication, MR, MB, ML, and MOD are affine function of this variables. Okay? And if you want to simulate this, you will need this function to satisfy this 4 equation, linear equation. And it's easy to see that you cannot. This cannot be true. Okay? It's simply, you can write this, you have a 4 variable, B1, B2, B3, and you write this as a system of linear equations, and you observe that your system of linear equations has no solution. So it's impossible to have a solution.
So
Yes.
I have one question. So I understand that MR is independent of product of B1, B2 because
Yes.
of the distance argument.
Yes.
But so you also say MOD does not depend on the product of
Yes.
3. But so MOD is product of all vertices. So maybe I think similar distance argument is
It's a sum, where MOD is a sum
sum.
of this. It's not a product, it's a sum.
Yeah, but
So in order to have a product, this means that one of the terms here should be a product. Okay? So for example, Z9 maybe is a product. But Z9, if you look, Z9 is here. Okay? And Z9 is maybe close to B, to this one, but it's not close to both this and this. So it cannot reach together a central point. Yes, it's a very important thing, that you don't have products. Okay? So you cannot do it with local, without long distance communication. And another way of saying this is that we have described a quantum process. It simply creates a graph state that sample from the distribution. And this quantum process only simply creates a graph state, so it can be implemented extremely efficiently by a constant depth quantum circuit, actually even using nearest neighbor topology. You only need to interact with your nearest neighbors in order to create that graph state corresponding to the. While this thing is essentially saying that any nearest neighbor classical circuit sampling from that distribution must have linear depths, because it should generate very long communication. So using this result, which is appearing in the paper I mentioned, 2007, this fairly old paper, you already get good evidence, unconditional evidence of the superiority of quantum computation if you are okay with a lower bound for nearest neighbor classical circuits. Classically, you can do it in constant depths. The quantum mean constant depth, and classically you need linear depths if you require that the classical circuit should be nearest neighbor. You can only communicate with your neighbors. Yes? Yeah, you need to close the line. Yes, so it's a little bit not really clear what I mean here by nearest neighbor. By nearest neighbor, I really mean, so you have your wires, but I assume that this one is also neighbor of this one. Yes, it's a periodic. So I'm a little bit cheating. It's not the standard nearest neighbor. It's something very close to the standard one. So it's on the ring. You can think of this. Yeah. This one is also neighbor of this one. Okay. Yes, it's a periodic. So I'm a little bit. But anyway, this nearest neighbor thing is not the main object of what I would like to talk today. I would like to talk about that result. And that result says similarly that there is a gap. Again, the depths required to solve a problem, but this time the lower bound holds for any classical circuit. So we are not talking anymore about the nearest neighbor topology. We don't have any constraint on the topology of the classical circuit. It can be any classical circuit. Okay? And what they have shown is that, so there is another computational problem that I will explain in a few minutes, such that, again, you can solve it quantumly in constant depths, but classically, any classical circuit requires logarithmic depths. Okay? So this gives you a separation. And again, there is no assumption, no conjecture here. It's unconditional separation. Okay? So you are losing a little bit here. The depth is log n. In the previous slide, it was n here, the lower bound n. But we are gaining a lot because we are not restricting at all the topology of the classical circuit. We are losing a little bit here. The depth is log n. In the previous slide, it was n here, the lower bound n. Okay, so I will explain this. So the problem is actually very easy to describe. So you consider a square grid of n nodes. Okay, a square grid of n nodes. So like this. So here I'm assuming that n is a power of 2. So you consider a square grid of n. And I will write m as the number of edges. Number of edges is essentially 2m, 2 times n plus minus something. So same order as n. And the input of the computational problem I will now define is a pair AC, where A is a binary string of length n, and C is a binary string of length m. And the input of the computational problem I will now define is a pair AC. Okay. And the computational problem we'll consider asks to sample from a distribution corresponding to measuring a graph state specified by the string A in the basis specified by the string C. So I will explain what this means. And instead of giving you the formal definition, I will work this on an example. It's extremely simple to understand on an example. Okay, so assume that you have n equal 9. So you have a square grid of n nodes. So this. So in that case, how many edges do we have? 12 nodes. This means that the input will be a pair A, it should be C, sorry, it's not B, C here. So it should be A and C. So A is a binary string of 9 bits, and so C is a binary string of 12 bits. Okay? And A, the string A, specify a graph state. And the string C specifies the basis. So what does it mean? Let's consider B, specifying the graph state. The meaning is that you look at the position where you have a 1. So you have a position, 1 at position 1, 2, 4, 5, 7, 9, 10, 11. So you keep only the ages with this number. What does it mean? You have 12 ages here. You assume that you have a labeling of the 12 ages in arbitrary order. And you keep only the 1 corresponding to the position where you have a 1 here. What does it mean? So this means that the graph specified by the string C here, this string is this thing. I'm keeping this age, this age, this age, this age, the 7, the 9, the 10, and the 11, and this gives you this subgraph. Okay? A. What's the meaning of A? So A specify maybe I'm sorry, I'm a little bit. It should probably. So yes. So sorry. So yes. So it's yes. So A. So the string A. So the graph state is specified by the string A. So A should be this. Yeah, so it's, sorry, it's a little bit. A should be here, just, and this should be C. So the graph state is specified by the string A. So A should be this. And A should be here. Yeah, sorry. And this should be C. Yeah. I mixed here. Okay, so this is this. So A is a string A. So A specifies the graph state, so it's this one. And C specifies the basis. Okay? So here you have a 1 at position 1, 2, 5, and 7. What does it mean? This means that anytime you have a 1, you measure the qubit in the y basis, and when you have a 0, you measure it in the x basis. So here you will measure 1, 2, 5, 7 in the y basis. So this one, this one, this one, and this one in the y basis, and the other in the x basis. So you do this. Okay. So this is the point of this definition. You use the first string to specify the subgraph of the square grid that you are considering, and you use the part C to specify the basis you are using. Okay. So now, let's describe, again, let's come back to this. So this is a computational problem. I just defined it. So now the first part of the theorem says that there is a shallow quantum circuit solving this on all inputs. Okay? Of course, because the problem is defined like this. The problem has to sample from the distribution corresponding to measuring the graph state in the basis. So if you are able to create the graph state, it's over. And we know that in a quantum setting, a graph state on a graph of constant degree can be constructed in constant depth. So this graph has, of course, constant degree. Any subgraph with also, yes. Yeah. Sorry, the degree is the number of edges going out any node. So here this node has 4, degree 4, and this is the maximum. Yes, so for example, the point is that I'm considering the largest degree of a vertex in my node. So here the largest one will be 4. The largest degree will be 4. in my circle it was 2. So now it's 4. Okay? So anytime it's constant, you can construct the graph state in constant depth. This is very straightforward because you have only to interact, this one has only to interact with its 4 neighbors. So this can be done really in constant depth. And now I need to show that classically also it's hard. This is the main part of the proof. Showing that it's easily quantumly, it's fairly trivial because we designed the problem so that a quantum computer can do it in constant depth. So I need to show that classically you need a logarithmic number of a depth logarithmic in order to perform the computation. And the proof is a little bit subtle, but the idea can be summarized fairly quickly. So you consider any classical circuit of small depths. And the goal will be to show that this circuit, which has small depths, cannot solve your problem. Okay? So the circuit has n plus m input wires and n output wires. Okay? So you have a circuit here. A circuit. So if I consider, for example, n equal 4, I will have this graph, this grid, and I will have so I have m equal 4, and I have A1, A2, A3, A4. B, it's B or C, C1. And I have A1, A2, A3, A4. B or C. Something like that. Okay. So I have n plus m input wires and n output wires. And I will associate to each of the first n input wires the corresponding node on the grid, and associate to each of the n output wires the corresponding node on the grid. Okay? So I will associate wires with nodes on the grid, and you use a central fact in circuit theory, that is that the classical circuit of small depths, in the classical circuit of small depths, so each input bit can contribute only to a small amount of output bits. Okay, because the depth is small. So if the depth is small, each input bit can contribute only to a small number of output bits. What does it mean? It means that, so if you write the relation between the input bit and the output bit in the circuit, so for example, the input bit corresponding to this node. This input bit could only contribute to a few number of output bits. So there can be only a small number of interaction between this node and the other node of the grid. And it's the same for all the others. So each node can interact only with a few number of output bits. So you will have only a few long distance communication if you look at the correspondence and between the input bit and the output bit on this grid. And what does it mean? This means that there exists a long cycle on which no long distance communication will occur. For example, here, this one. If the only long distance communication on this grid are the one depicted by the arrows here in green, then you have this red cycle. And in this red cycle, there is no long distance interaction, communication between nodes on the cycle. This one communicates to this one, but this one is not on the cycle. And so on. So this means that if you consider the string A that specifies this long cycle, then the task will be to sample from the distribution corresponding to this graph state, the red graph state. Okay? And then you cannot do it. You cannot do it exactly from the same reason I explained in the first part of the talk. You have a long cycle on which there is no long-distance communication. And I ask you to simulate what's happened when I measure the qubit of this graph state is some basis, depending on your input. We have shown in the first part of this talk that this cannot be done classically if you have no long-distance communication. Okay? So this cannot be done. So the conclusion is that you cannot sample from that distribution if the classical circuit has small depths.
So you constructed a circle where no long correlation occurs.
Yes.
But maybe is it possible that so this cycle still has some long range correlation, but this amount is not enough or something like that. Maybe now your cycle is completely avoid.
Yes.
Long, but maybe small amount of.
Sure. And this is actually, so you can, this is what's done in a more recent version of the paper by Bravi, Gosset, and Koenig, actually. So the original argument is that you can completely avoid everything, and this gives you a hard case, but you're right, there are other ways of obtaining an hard case. And I will come back to this probably at the very end of the talk. Okay, so what they showed here, so it's exactly the argument in their paper, they show that any classical circuit that solved this problem on all inputs should have logarithmic depths. Why? Because if you have a small depth classical circuit, then there exists an input such that the circuit does not work. So it's really a worst case hardness argument, the way I presented it. You fix your classical circuit, and you say, there exists a path where there is no long-term correlation, so I will choose a A here in my input so that this happens. And then it's impossible to do the simulation. So there exists an input for which the simulation is impossible. It's a worst case argument. It does not give you average case complexity, only worst case complexity. And then it's impossible to do the simulation. So there exists an input for which the simulation is impossible. Okay, so lastly, how to obtain our result, so the average case hardness. We can do it by introducing a new construction. So I call this the extended graph construction. But actually, well, something very similar have been also introduced in prior works, especially by Fujis and Mori-Mason. So you have this kind of construction. So you take any graph, and you add one vertex at the middle of each edge. Okay? This is what I call an extended graph. From any graph, I add one vertex at the middle of the edge. And I get what I call the extended graph of this graph. And we will use it for the grid, the square grid. Okay, I have my square grid, and I add one vertex here at the middle of each. So I obtain this. It's the extended graph corresponding to a square grid. Okay. So now, consider any cycle of the graph. So here I have a cycle in red. Maybe it's a little bit difficult to see if it's here in red. Okay, this cycle, long cycle. And I will divide it into three parts, like a triangle. So this top side, this right side, and this left side. Okay, so I see it like a triangle. And I will define a computational problem on it, very similarly to what I did before. So each of the three corners gets a bit as an input. And each node of the graph will output a bit. Okay? And the output will be defined like this. It's essentially the same as before. So the node first prepares the graph state corresponding to the whole graph, and then each non-corner node. Each corner node means all the nodes here which are not the corner, but also all the nodes here will do the measurement. Okay, so each node of the whole graph, which is not a corner, will measure its qubit in the x basis and output the outcome. And each of the three corners, so the three qubits, will do something slightly different. If their input is 1, they measure in the y basis, otherwise they measure in the x basis, essentially as before. And if you do this, what you get is this. So the quantum process samples for the uniform distribution over all binary strings satisfying this condition. It's very similar to before. You have 4 possible conditions. It looks very similar here, but the difference is the definition of all these bits. Okay, so n, what is n? N is the total number of vertices of the whole graph. So everything. Okay. All the blue vertices and all the green vertices of everything. M all is the parity of the outputs of all the blue nodes. All the blue nodes, even outside the triangle. MR is the parity of the output of the green node, only the green node on the right side of the triangle. So in this graph, it's this, and this 3. MT, the parity of the output of the green node in the top side. So you have this, and this. And MS, the parity of the output of all the green nodes on the left side. This, and this. Okay? And you can show that if you do that process, what you get is exactly this. Uniform superposition of all strings satisfying these conditions. It's fairly similar to previously. But the main difference is that we are using a graph that is not the same. Before you have only a triangle. Here you have a triangle embedded in a big extended graph of a grid, of a square grid. But you obtain fairly similar conditions. So it's not surprising that you get essentially the same impossibility result, classical. That any classical protocol that sample from the same distribution will require long-distance communication. Okay. And the proof is essentially the same. Okay. So if you don't have long-distance communication, you will have a affine function, but you won't have B3 here, you don't have B2 here, you don't have B1 here, and if you look at the system of linear equation needed to satisfy that, it doesn't have any solution. So it does not work. If you don't have long-distance communication, you will have a affine function, but you won't have B2 here, you don't have B2 here, you don't have B1 here, and if you look at the system of linear equation... Okay, so just to finish, let's go back to the proof of the lower bound in the paper by Bravi, Gosset, and Koenig. So remember, the point was that I have a cycle on which there is no long communication. So Bravi, Gosset, and Koenig wanted to use the result I mentioned at the very beginning of the lecture with the triangle. So they say, let's remove everything else than this long cycle. And that's why they obtain a worst case complexity. But the point is that, no, we don't need to do this. Because we have a new impossibility result, which is not only for the triangle, it's for a triangle embedded in a square grid. So we say that if you don't have local communication, long-term communication on the cycle, it's impossible to do it. Okay? Even if it is not only a triangle embedded in a square grid. So there is absolutely no need of selecting only the long cycle part. You can keep everything as it. Okay? So this enables us to define a problem where you have only one string C. You don't have A as before. You have only C. Okay? You don't use part of the input to specify the graph state we are working on. We work only always on the whole graph state, and you only use the input to specify the basis with the basis you will use to do the measurement. Okay. And then you can show that, of course, you can still do it with a constant depth, but you can show that classically, then any classical algorithm that solves this problem on a non-negligible fraction of the string C should have log of the triangle, but for a triangle embedded in the square grid. Okay, so this graph state, actually I was lying a little bit. For technical reason, this does not work on the square grid. I need to consider a graph a little bit more complicated, and this is essentially the graph we are using. So it's not really a square grid, it's very regular, but you have some vertices with degree 8 for technical reasons, because you need to find a lot of paths, many paths going through the same vertex. Okay, but it's constant depth. It's a constant degree, so it can still be done quantumly with constant depth. Okay, so to finish, so I said that I will talk a little bit about the relation with the concurrent works. So the prior work by Breivik, Gosset, and Koenig was this. So they said again that it's a worst case classical hardness. So no constant depth classical circuit can solve it on all input. What I have shown is that no shallow classical circuit can solve it on a non-negligible fraction of input. So it's a stronger result. Okay? Average case classical hardness. But actually, so this is the archived version. And last year in November, they had a paper published in Science. And in Science, there is a supplementary materials. And if you look very carefully in the supplementary materials, it's a very, very long appendix, there is one section that actually gives an average case classical hardness result. But it's only hardness for a constant fraction. Ours is a little bit stronger. Okay, so it was published in October last year. Also, at the end of the year, last year, another paper by Kudron, Stark, and Vidic showed exactly the same statement as here, with an application to randomness expansion. But they use it using a different construction, not the same as ours. And almost at the same time, another paper by Bennett, Kotari, Schafter, and Tal, well, it's unpublished, but it was accepted to QIP, so it was submitted also in October last year, gave actually the same statement as mine and this one. And an additional result is that it holds even against classical circuit with unbounded fun. So we have essentially 1, 2, 3, 4 versions of average case classical hardness that appeared during the same period of 1 month last year in October. Okay. All using actually different construction, but achieving very closely related statements. Okay. So to conclude, so this is what we did. So average case quantum advantage using shallow circuits. The point, again, is that it does not rely on any conjectural assumption. Okay? It's complete proof, unconditional, nothing assumed. First open problem. What about quantum supremacy with noisy quantum computation? Because the part 1 says there is a good circuit, a constant depth circuit that solves the problem. Yes, but actually that circuit does not solve the problem when there is noise. Okay? So it does not say anything about the quantum supremacy in the noisy setting. So you would like to have a statement which is robust with respect to noise. But it has been done actually very recently. So it's appeared on the archive a few months ago. So Breivik, Gosset, Koenig, and Thomas Michael showed that actually a noisy version of this theory using error correction techniques. It's not surprising, but it's fairly technical because in order to do error correction, typically you need logarithmic depth. And here we are in a setting where you want to do everything using a shallow quantum circuit. You cannot allow logarithmic depth. So you have to use a few tricks. But their paper is for loci nodes, so you can ask what about more general version of nodes. The second open problem is showing advantage against stronger classes of classical computation. Because the statement here says that no shallow, so no constant depth classical circuit can solve the problem on a non-negligible fraction of the inputs. But a logarithmic depth classical circuit can solve it. So this problem is very easy actually. You cannot do it classically in constant depths, but you can do it in log depths. And log depths is very easy. Of course, polynomial time, you can do it in polynomial time, but even stronger, you can do it using log depths. So it's a very simple circuit. The circuit is a very simple problem. You cannot do it in constant depths, but you can do it in log depths. So it will be very nice to find a problem that can be solved by a quantum shallow circuit, but cannot be solved even with a classical circuit of logarithmic depth, for example. Okay? To obtain a stronger classical lower bound. It will be very nice. Okay? And especially, yes, so breaking this log barrier. Maybe it's the limits of what we can do without any assumption. Okay. Because our technique essentially says that the reason why classical computation cannot do it is because classical communication should establish some kind of communication between all the nodes or all the wires. And this requires log depth. Okay? So this may be the limits of all the argument we are using here. It's very important to try to understand if we can break this logarithmic barrier. Okay, I think this is all what I wanted to say. So thank you for your attention.
Okay, thank you very much. Is there any question or comment? Okay, thank you very much. Is there any question or comment? So about open.
So the problem arose when you require the classical circuit to have if you require to have only a small number of long-range connections, then you cannot do it, right? But small in that context just means that it doesn't scale with n, right? Or not? What does small mean in that context? So it's order 1 or?
No. It means that you can, for what we need it to be small enough so you can find the largest cycle on which there is no long communication. So if it is smaller than n to the power something, it's okay. If it is n squared, it's bad, because n squared means that you have communication between any two nodes. It will be bad, but you have n to the power 1.5, it's okay.
So anything smaller than n squared is already...
Anything smaller, strictly smaller than n squared should be okay.
Okay.
So it's a very weak, yeah.
Thank you.
It's great.
The question or comment?
So maybe this is a little bit stupid question, but so what happens if you change the graph to the graph with like log n what is that, degree? Then can you say something like there is a log n quantum circuit that can solve the problem easily, and
So
it cannot easily.
If the degree is log n,
Yeah.
quantumly, I think you will need log n depth.
Okay. Then can you say something similar to to solve the problem classically?
I think that classically you will still have, you need logarithmic depth.
Logarithm depth.
So you will obtain the same classical lower bound and a weaker quantum upper bound. So it will give you a worse result. You need more resource quantumly, and classically you need the same amount of resource.
Okay.
So it's, yeah.
Good. Yeah. Thanks.
Any other question or comment?
You need the same amount of resource.
Okay.
So it's,
Good. Yeah. Thanks.
So about open problem too, what do you mean by more precisely? Because so maybe you don't believe that you can show that your problem cannot be classically solved in classical polynomial time without any assumption.
Yes, it's a good question. So actually, one partial solution has been given in the prior work here. So for example, this is one possible answer that's already been done. What we did here says that any shallow classical circuit that uses gates of bounded Fannian, so gates where only 2 input and say 2 output. Here they show a stronger result. They say that you need even log depths if your classical circuit is able to use gates with unbounded Fannian, an unbounded fan-out. So this is the kind of things. So maybe you will try to there are a lot of classes of circuits in classical circuit complexities. Of course, we cannot expect to prove a result for polynomial size or polynomial time because it will prove separation between BQP and P. It will be too much. But there are many possibilities here, allowing maybe more general kind of gates in the classical setting, maybe not log depths, but log square depths, or something like that.
The reason why your problem is easy for polynomial time classical computing is what you are doing is XZ basis measurement on graph state, which is just Clifford quantum computing.
Yes.
So maybe one idea is just you also add some pi over 8 angle measurement.
Yes, maybe yes.
In this case, you can no longer use
Yes. But another question is, in that case, how to prove that it is hard. Because the point is that this technique works for non-locality reason, and log it seems a barrier for all that. But it's true that by doing these kind of things, it's maybe even difficult in the classical setting.
And can you go to the open question part? You talked about the local errors. Yes. In Bravi's paper. What do you mean by general version of noise?
Yeah, I mean, this local version is extremely general one, anyway. So I think for physicists, the local noise, it's perfectly okay. You can consider, what I would like to consider is what I call adversary noise. So I can kill, say, 1% of all your qubits. I'm not assuming any locality in the noise. Of course, it's probably not physical, but what about this kind of models, where you are really some kind of arbitrary noise? You are allowed to put noise on any qubit of your choice. So is it possible to show quantum supremacy for this very, very strong version of noise? So there are a lot of other things that you can do. But I agree, probably for physicists, local noise it's still enough. It's already enough to be able to talk about the supremacy with noisy quantum computation.
Okay, any other question or comment? No? Okay, then let's thank the speaker again. Okay, so now finish all talks in this week. And so now we have a 30 minutes coffee break. And as I said, after coffee break, if you are very kind, please help us to bring the poster board to the next building. And also, if you did your poster presentation and you still put your poster on board, please take that. Is there any other announcement? No? まあ、来週に、じゃあ、OK。So, let's take a break.
そうですか。いや、いろいろと。